Hello everyone. This is going to be a little bit of a strange episode. You'll notice that the things that I'm saying are not in sync with the video of my head. This is because for this particular episode, for some reason, the microphone audio did not get recorded correctly, so I'm going to have to overdub this with my after the fact commentary. And so I'm just going to watch this video and talk along over the top and sort of ad-lib what we're doing. So first of all, obviously, I'm checking what we did in the previous week and checking that the shader that we tested out worked correctly, and sort of just revising the fact that text coordinates obviously go from 0, 0 in the top left-hand corner to 1, 1 in the bottom right-hand corner. And I know in a second I'm about to draw that exact diagram. And so obviously what happened earlier, the gradient in the picture before changed the red channel on the x-axis and the green channel on the y-axis, and which is why you got that picture. And so obviously when you're drawing something on the GPU, if we're drawing a sprite, it actually is a pair of triangles that gets rendered, and those triangles have the correct text coordinates set on them. Obviously what I've just drawn here, the UV is often what the text coordinate is called, and it goes from 0, 0 in the top left to 1, 1 in the bottom right for your standard texture, and that's also sort of the standard coordinate system for Sprite Batch. So there's the there's our test shader, which the source code for that was displayed at the very start of the video, and I think I'm about to open it up again, and so you can see here we're multiplying by the original texture, which is a white texture with a black smiley face. So the black, black is obviously 0 multiplied by some value gives you black, but the white multiplied by some value gives you this gradient. And I've removed the blue channel there. I've set that to 0 so you can quite clearly see that the U coordinate, which is the X coordinate of the text coordinate, goes from 0 to 1, which causes the red to go from 0 to 1 as you go horizontally, and obviously the green to go 0 to 1 as you go down vertically. So I think what we're doing here is pulling back that test code that we did at the end of the previous lesson, which produced this quarter circle. And so that's generally what this particular lesson is going to be about, is talking about the how and the why of making a circle like this. So let's see what's going to happen. So first of all, I'm just going to have to watch and see what I actually drew at the time. Fixing up my drawing canvas, obviously. I have no idea what I was saying. Oh yes, I remember now. What we're going to do is we're going to talk about distance calculations, or the length of a vector. So say we've got a vector at, say, the coordinates 3, 3. I suspect possibly Daniel's asked me a question now. Daniel's audio actually made it into this video as it was recorded, but obviously it's a bit useless to just have like half of a conversation going on. So I've decided that it's easiest thing is to just cut that bit out and do my best to make do with commentary over the top. So say we're doing the length of a vector that's 3, 3. So what I'm going to do now is let's try and code that up. So if I've got a vector foo, which is x equals 3, y equals 3, and I get the length of that by calling the length function, I can stick that in a variable length. And what I think I'm going to do now is run this piece of code, and actually we'll be able to mouse over and get the exact length, which is 4.24. So that tells us the length of a vector, and we can actually hit F12 on that function to go to the definition, and we can see the length function is, and I'm going to draw it now, is the length of a vector is equal to the square root of x squared plus y squared. And if you're working in more dimensions than that, it actually, if you have 3 dimensions, it's the square root of x squared plus y squared plus z squared. So the square root of, I don't know why I wrote the square root of 4.2 there, because obviously that's already squared. So I think I've made a mistake drawing on the canvas. So it should be 3 squared is obviously 9 plus 3 squared again, which is 9. So square root of 18 is 4.2 whatever. And so obviously that's the length formula for any vector. And the way that we derive this is something called Pythagoras' theorem. And so we can draw this out. So if we've got a triangle, we know a right angle triangle, in fact, we know that one of the sides of the triangle we can call that the x-axis, and the other side we can call the y-axis. And if we take the squares of those two sides, as I'm sort of drawing out geometrically here, we can say that that is equal to the square of the hypotenuse of that triangle. So this is how the length formula is derived. Now there's probably there's definitely a more involved way of figuring this out, but what I'm going to go on to talk about in this video here is so you add those two squares together and you get the area of the hypotenuse squared. So what I'm going to go on to talk about is there's a science museum in my city, which I've been to several times, obviously growing up and all that. And what what they had at this museum was a device. It was basically a big circle with this diagram on it, and you see that sort of green dot I put in right in the center there. That was the axis of rotation, and it was a rotating device with this diagram drawn on it, and the each sort of squared section was hollow, and so the whole device was filled up with water. Well, I guess just the squared sections were filled up with water, and the triangle in the middle was obviously solid. And so what you could do to basically prove this theorem is you could rotate the device, and if you rotated it into a position where the two square sides are down, those two squares would be filled in with water. And then what would happen if you rotated that device so that the larger hypotenuse squared side was facing down, then all of the water from the x squared and the y squared sections would fall down and fill up the section which is the hypotenuse squared. And so that was the proof that the area of those two squares is the same as the area of the hypotenuse squared. And so it's an interesting device, and I guess that's just a bit of an interesting tidbit about why that works. So moving on now, I think we'll see what I draw again. So now let's say that we want to consider. I'm trying to remember what I'm going to be drawing here. I think we're just considering any vector. And what we can say about these vectors is that for a given length of the vector, we can basically inscribe a circle. So all of the vectors of a certain length, which is the same length as that first vector, will form a circle. All of the vectors that are of the length of that second vector form a different circle, and obviously we can form a circle here. And obviously drawing a circle by hand sort of in that direction is not trivial. Not the best artist here in this video, obviously. So what we can say is the a circle is basically all of the vectors of a particular length. And furthermore, we can say that well, we'll go on. Okay, so what obviously I'm doing here is I'm going to define this circle as being of radius 1. And so all of the vectors of length 1 define that circle. And also we can say that all of the vectors of length less than 1 will form the inside of that circle. So if we want basically all of the vectors inside that circle, so a filled circle, they're going to be length less than 1. If we want all of the vectors that are outside of that circle, we want all of the vectors that have a length greater than 1. So I think I'm just saying that what we're going to do is we're going to focus on vectors of length less than 1. So what I'm drawing here is basically every vector that is of the form x squared plus y squared, sorry, the square root of x squared plus y squared is less than 1, gives us all of the vectors inside that circle. And what we can further do is we can we can remove the square root sign by squaring the opposite side, and obviously 1 squared is 1, and I think what I'm about to draw here is that we can say that less than radius squared. So all of the so if we want a circle of some given radius r, this is the formula for all of the points inside that circle. So x squared plus y squared is less than radius squared, and this works with all of the signs. So you can have a less than sign, or an equal sign, or a greater than sign, or a less than or equals to sign, and so on. And they just define the different spaces. So inside the circle, outside the circle, and on the circle itself, like on the perimeter of the circle. So now what we want to do, I believe this is why I've drawn a square, is we want to I think that's what I just explained, why I drew an equal sign, is that's why we might do an equal. So this sort of tells us if we have a vector, does that vector satisfy this condition? So what we can do is when we're on the GPU and we're testing a pixel in a pixel shader, we can test every single vector. And we can say, does the vector satisfy this condition? Does it satisfy the condition x squared plus y squared is less than some radius squared? And that's what we're doing here with our texture, our pixel shader that's working in texture coordinates. So it's obviously the top left is 0, 0. It goes down to 1, 1, and we test. We get basically a radius squared, which is v in this thing, and see if v is less than 1. So what am I doing here? I think I'm considering, yes, okay, so we have v, which is the length squared of the vector. I think I might rename that here. Yeah, so you can see that I'm sort of considering my variable names, which is obviously important to make sure that it helps to name things properly, because v is a bit ambiguous, and calling it r would have been a bit ambiguous, whereas radius squared or even r squared would have made a lot more sense. Anyway, so this is the little formula that we have, which is, if it's less than, we're going to be white, and if it's greater than, we're going to be transparent, and obviously transparent on our black background. And we draw a quarter circle. And so I think what's going to happen here is I'm going to hand over to Daniel and let Daniel draw this out and basically catch his code up to mine. I think Daniel might be asking me another question at this point. Unfortunately, I'm not sure necessarily what that question was at the moment. I think it was, in fact, about why the background color is different, and so yeah, there I've gone ahead and I've changed the background color. In fact, I'm not sure, in fact, whether I drew that transparent or black originally. You'll have to rewind and look at the code and see what it said. And so, yes, and then we had a quick discussion about the orange. I'm passing an orange there, and why is that like that? And then obviously I'm clarifying what the radius is. So if I put in a radius of 0.5, we get a circle with a radius of 0.5. What else are we doing? Yes, and so at this point I am increasing the size of the thing being drawn just so we can see it more clearly. Do I increase the size again? Yes, I do. Just so I can get a nice big graphic. You know, bigger is better. And yes, don't mind me while I guess talk to Daniel here and you can't hear it. So yes, so there is a point to oh yes, okay, so we'll talk about the point to that later, but so what I'm describing here, there's a website called shadertoy.com, www.shadertoy.com, and what it is basically it's like a bigger and better version of what I've just been doing. So I've drawn a circle using some maths, using just a formula for a circle, and if you take that and you expand upon that concept, you can draw a great many things algorithmically. So there's obviously this Kirby here is made up of a lot of probably spheres. I haven't actually read the code here, but I'm just scrolling through it so you get an idea of, you know, there's actually not that much code there in order to draw this image that you see here. So someone's very carefully gone through and placed all of the circles and the gradients and so on to make this shape. So it's just an advanced version of exactly what we've been doing. So it's quite a powerful technique and you can take it very far. So let's see, we're going back to the whiteboard now. And making a new layer. So what are we going to talk about now? This is an excellent question. Yes, so obviously we're drawing our circle in the top left corner. Obviously we're drawing a quarter circle rather than a whole circle. But for our line drawing thing that we've been working on, we actually want to draw an entire circle, just like the if you've been watching along with the series, the texture that we have is a texture of a full circle. So we want to have between the texture point of 0, 0 to 1, 1 a complete circle. And what's going to happen is when we draw our line sprite, we've got 6 triangles if you recall, and you know, 2 of them will form the center of the line, the sort of main component of the line, and they'll be filled in completely, whereas the 2 end caps are going to be half circles. Now, I think I may discuss this at some point here, and that is we could, in theory, you know, we could in theory change the text coordinates that we're drawing, so that the sprites, and yeah, here you can see obviously we're drawing that half circle, and you know, it's you know, it's all pixely and so on, because it's a texture. We don't have that infinite zoom that we'd have if we were drawing it algorithmically. What was I saying? So yeah, we could actually adjust the mesh, the texture coordinates of the triangles we're passing over to the graphics card, such that we just use that circle effect to draw the full circle. But there's one reason that we might not want to do that and actually adjust our pixel shader to draw the whole circle within the standard texture coordinates, and that's just so that our pixel shader matches up with the texture. And so that could come in useful if, for example, the you wanted to be able to toggle between the texture and the pixel shader, for example. Anyway, we're looking at intrinsic functions here. So if you search for HLSL intrinsics, you get this list of intrinsic functions, which these are all of the built-in functions in HLSL. So we want the step function, I believe is what we're looking for, which is returns x greater than a, returns 1 or 0. So that's an alternative function that we can use rather than putting a if statement into the pixel shader. So we're going to replace that conditional with the step function, just to make things a little bit neater, and obviously to remove that if statement. You'll also notice, if you're looking really closely, Daniel does have a typo in his code at this point, and we'll catch that in a minute or two when his circle doesn't draw. So try and spot it now. It's a simple typo. So you can see what I'm doing here is I'm using the step function to get a value from 0 to 1 based on what the circle is. And I've just changed my mind from using the full, expanding that out and just returning it, to actually using the color that gets passed in, because I mean, if you can color your circle when you draw it, why not? We're going to need that functionality later. So you'll notice, if you noticed before, whereas passing orange into the shader, that's why that circle's coming out orange. So I'm going to go back here and just change that to white for now, so that we can see exactly what's going on in our pixel shader. So here's the white quarter circle. And yes, so you'll notice that Daniel's circle is not quite a circle. It's the shape is a bit interesting, and I mean, that could be a useful shape sometimes, but obviously not a circle. So just give Daniel a moment to fix up his typo. Obviously, yes. So there is a power function for power in HLSL, and a typical decent compiler for HLSL should convert, if you say power, value comma 2, it should convert that to a straight up multiply. But obviously the power function is more expensive than a multiply, so it's sort of kind of a bit of a habit from writing just raw instruction based shaders, where you just, rather than do a power function, you do a multiply. Sort of a holdover from that, and it just makes it really clear that you are doing a straight up multiply and not something more expensive. So what we're doing here is we now need to move our circle over. So we've got the circle, we've got the bottom quadrant of the circle basically, and we want to get the whole circle. So in effect, this is what we are starting with. We have a circle centered at 0, 0, and of radius 1, and it goes obviously from -1, -1 to 1, 1. Yes, and so at this point in the video, this is where I'm explaining that we could in fact change the text coordinates that we're passing in with our triangles for these lines, but obviously it's kind of nicer just to use the same text coordinates as a texture, because then we can just flip between the two trivially. So we need to make that transformation that lets us draw that. Yes, and so if we are sampling a texture, we kind of I guess, yeah, so there's this a thing called a sampler state, and that tells us how we're going to sample the texture. I think Daniel must have asked this as a question. And so we can choose various forms of either wrap or clamp, and if we pass in wrap, then we're going to get 4 copies of that texture if we were to change our texture coordinates. So we'd get obviously, yeah, we'd get that repeated as we went into negative text coordinates. Whereas if we said clamp, we'd get a single copy between 0, 0 and 1, 1, and then we just get the edge pixels of that texture as we went outside the standard 0, 0 to 1, 1 text coordinates. And so I guess if you're watching along at home, that's something you can very quickly prove to yourself, I guess. If you try passing in text coordinates to a drawer function outside the standard range, and you switch your sampler state between clamp and wrap, you'll be able to see how that functions. But it's fairly straightforward. It does what you would expect. It either clamps or wraps as it goes outside the range. So now we're just constructing the transformation that will take us from this sort of -1, -1 to 1, 1 texture space to the same shape appearing in the sort of 0, 0 to 1, 1. So the first thing we need to do is we need to move our circle, the center of our circle, from 0, 0 to 0.5, 0.5. So you can see that, you know, halfway between the 0, 0 and the 1, 1 is 0.5, 0.5. And what this does is it has the effect of moving our shape to appear in the space from 0.5, sorry, -0.5, -0.5 to 0.5, 0.5. And then you'll see I've kind of slightly confused myself in this video by saying UV equals UV minus whatever, which sort of doesn't make that much sense mathematically, but, you know, if we're writing code, we know let UV equal UV minus minus half, I guess. And I'm just clarifying that in our code we've called the same thing as UV, we've called it text coordinate. And obviously if you've, I guess, put this tidbit in here, if you've got a 3-dimensional texture, you might, you know, your text coordinates would be UVW. And then and the reason for that is obviously that, you know, if you've got a 3D coordinate, it's XYZ, so, you know, the previous letters would be, you know, UVW XYZ. And that gets a little bit confusing because often when you're working on the GPU, you're actually using 4-dimensional coordinates. So you might have seen us using XYZW, where the 4th coordinate is the W coordinate, and that comes in handy sometimes. And obviously if you're working with colors, you know, your XYZW is red, green, blue, alpha. Yeah, so here you can see I'm trying to unconfuse myself by sticking the little colon there to indicate let UV equal that rather than UV equals that. I think I have the colon on the correct side. Obviously, in the languages that I tend to use, the colon is not included. And so obviously we've constructed this thing where we're taking UV, we're subtracting 0.5, 0.5, and then we're multiplying it by 2 to scale it up to the correct size. And so if the maths has worked out correctly there, we can now go back to our effect that we were working on, and we can open it up in Notepad++, which is the reason I use that is because I happen to have a syntax highlighter for HLSL installed there, which is handy. So I've renamed the text coordinate to UV just so it matches what we wrote on the whiteboard, and we've just plugged that formula in, and we're going to run it and see if it works. Let's see what happens. And ta-da! We get our whole circle. And I think what just happened there is I just clarified what the multiplied by color was for. Same as when we were drawing an orange circle just now. And yes, so if I wanted to prove, for example, that you know, the circle covers exactly the area of the texture that we're drawing, so exactly 0, 0 to 1, 1 in texture coordinate space, I can just chuck a you know, add some value to the red channel onto the end there, and that will give me a bit of red in the other channel. Now, one of the reasons I can do this, I remember explaining this in the video, I'm not sure when exactly, but the reason that this is possible is because the output of the shade, in fact, this is exactly what I'm doing here. If I'm returning a value that's, you know, I've added 1, but it was already 1, so it's now 2, I'm returning this 2, 1, 1, 1, 1 value. But when that goes out to the screen or out to the blend stage of the shader, unless you're working on, I haven't really done it much, but I think if you're working on a floating point surface, then it will actually store values outside the range 0 to 1. But if you're working on a standard surface, it will actually saturate, which is this function here. It will automatically saturate that value for you. So, you know, I can send 100 out in the X channel, and it will saturate to the correct range for output, which is why I could get away with that. But that's just some extra thing just to show that I guess that's the correct circle, even though the edge is transparent, so it's not showing up. You know, it's indistinguishable from the background color of what we were rendering. Not sure what I'm laughing at there. It's probably funny. So I think I figured out what went wrong with my microphone, and that is it was stuck in a I put it in a USB 3 port, and oddly enough that didn't work. So yeah, so I was just showing off a thing that we were working on earlier, which was I made a sort of CRT shader for River City Ransom, and to get the nice rounded corners on the screen, I used a shape called a squircle. So it's sort of a combination between a square and a circle. So to make a circle, you recall, we have this function. We've got circle equals x squared plus y squared. So the squircle is x squared, x to the power of n, y to the power of n. And so as you increase the value of n, you get closer and closer to a square. And oh yes, and I think you have to take the absolute value of x and y, because obviously if you've got a negative, if you've got a negative value for x or y and the power you're taking is not even, you could end up with a negative value, which is not what you want. So I'm just coding this in here just to give an example of a thing that you can do that sort of takes you one step closer to that Kirby thing. It's like, you know, you can make more shapes than just circles using this technique if you know the right formulas and stuff, and obviously you can take it quite a long way. and I just made a typo there. I've done squircle times circle, which is, you know, that's a fun shape right there. It's, you know, maybe that could be interesting for something. Let me just find my mistake. So I also haven't done the step function. Here we go. So there's step of squircle. So I want everything that's less than 1 or equal to 1 in my shape, and then multiply it by the color. So we'll run that and we'll get this squircle. So you can see we've got these nice rounded corners. So that's kind of how I did the that rounded corner effect for the screen in that CRT shader that we were showing off on Twitter. Now, in the actual shader, I used something called an FG squircle, and in fact, I used that as a starting point and actually modified the formula heavily to do some other effects. But that's sort of a starting point, I guess. And so yeah, here I am showing, you know, if you have n equals 5, the corners get less round. So there's one more shape you can add to your repertoire. And you know, if I set n to 100, we're going to get something that's very close to a square. So as I was saying, I think I've sorted out the issue with the microphone, and hopefully we won't lose the audio again. It was a bit unfortunate that we lost audio on this one. I think we're nearly done. We've got about another 1.5 minutes left of video. So what are we going to do? I think possibly I'm talking about what we're going to do next week, and that is as well as take our circle shader and make sure it's part of our line drawing system. We will also actually start doing some maths with circles, hopefully, that makes use of that factor. You can figure out whether a point is inside or outside a circle based on the radius, based on the circle formula. And also I think I'm talking about how if you look really closely at the circle, you'll see it's aliased. You can see it's kind of got jaggy edges. So there are things we can do about the edges of our circle just to make it a little bit smoother. But I'm not sure we're actually going to do that in a hurry because it's just a bit fiddly and requires talking about some maths that not particularly relevant to anything we're actually going to be doing in the near future. But hopefully we might get to it at some point, because it is obviously interesting to be able to do that anti-aliasing. So I think that's everything. So I think we've almost run out of video. So thanks for watching, everyone. Sorry about the audio problem, and hopefully that will be fixed for the next video. Hopefully having me just sort of talking over the top hasn't been too painful. What are we going to do? What am I doing? I'm switching to ImGui. So I think I talked at one point why that's called ImGui, which is sort of something Daniel was interested in. Anyway, I think we're done.